We're going to be talking about the constant velocity lab. In this video, we'll be talking about the purpose of the experiment, the free body diagram model, the fundamental physics principles that deal with this experiment, methodology, the graph, coding, some sources of error, and then some possible questions at the end. So this lab intends to compare an object's observed position versus predicted position at a constant velocity using tracker and glow script. In this experiment, the system is the object, which is chapstick, and the surroundings are the environment around the chapstick, such as the table that the chapstick was rolled on. This situation is modeled using this free body diagram, where the forces in the x direction, although opposite, have equal magnitude, and the forces in the y direction, although opposite, have equal magnitude, meaning that there is zero net force on the object. This lab primarily deals with Newton's second law, which states that the net external force on an object divided by time the force exerted is equal to the change in momentum. And through these equations, we can see this. So looking at the first equation, which is kind of the main equation, you can derive multiple equations as shown below. And finally, we can derive that the final velocity is equal to the initial velocity plus F net over m, which is mass, times time. And because F net is 0 in this lab, we get that the final velocity equals the initial velocity, which is the point of the lab, as velocity is supposed to be constant. Now to discuss the experimental setup and methodology. First, a cylindrical chapstick was rolled across a table and recorded. This video was then uploaded into Tracker to gain information about the observed position using small intervals of time. Then glow script was used to find the predicted position values. Finally, both sets of data, the observed and predicted, were graphed over time and then compared. Just to go briefly over the results of the observed position, we can see my screenshot from Tracker. So I tracked the chapstick using the center of mass. And as you can see with this curve of the position time graph, the line is pretty much has a constant slope. There is a slight curve though, which will be discussed later. However, the constant slope, or for the most part, the constant slope, indicates a constant velocity. So this is the overall graph data. As you can see, the experimental is represented with the blue line and the computational is represented with the orange line. So to start off with the similarities, they start off having the same slope and they both have positive slopes. However, this is where we get to the differences. The experimental line starts to curve concave down, as you can see right here, very slightly, and the differences between the two lines gets larger as time goes on. Also, the computational line does not start at time equals 0 seconds, which may have been due to a coding error. So now to examine the code that developed the computational model, we start off with the ball's position, and we find that number using the tracker data. We then find the ball's velocity, and we find this using the formula v final plus v initial over 2. However, the v final and v initial should be the same as velocity is constant. Therefore, the ball's velocity is constant. We then go into the F-net section where the F-net is 0, 0, 0, as the point of this lab is that the force is constant. We then get to ball velocity equals ball velocity, and this was done because the velocity is constant, so it does not change. Finally, we get to the position update formula where we use the initial position plus the ball's velocity times delta t, or the change in time, to update the ball's position in the graph. And using all of this, the computational model was developed. I will be looking for some possible sources of error that may have caused the differences between the computational model, the observed model in the graph. So basically, the first and foremost source of error was likely external forces such as friction. When the chapstick rolled across the table, it encountered friction that caused the velocity to slow down towards the end, which is what the curved line in the observed model on the graph was showing. There may have also been some issues with Tracker when tracking the center of mass, as I may not have accurately clicked on the center of mass each time. Finally, there could have been a coding error which may have caused that difference in starting time between the computational model and the observed model. So finally, for some additional questions, what if the plus x and negative x were interchanged? This would just simply cause the slope to be negative. Finally, is it possible to determine how many forces are combined to give the object a net force of 0? I would say no, because there are several different forces that are acting upon an object, such as gravitational pull of other objects, meaning that there's so many different forces acting upon our system, which causes too many forces to be accounted for.